Okay, guys, I think it's time, so we shall start. Come on, guys. Well, we're gonna stay on with the pure axial force type structure for the next two lectures. This time we'll move on from pin joint truss to cables. Okay. For today, we will stay with the cable subjected to point load. There's not much theory to be taught because actually we know how to work it out. But let's go through why we have to learn about it. Okay. Let's talk about an example. Okay. The reason this cable type structure has been the cable has been taught in this course and remaining being taught in this subject is because it's the basic of this kind of bridges. It's called cable stay. These are very good for the very last span structure, especially where you cannot put column into the middle of the structure. This is kind of like a bridge across a cliff. Okay. This is quite old bridge, a more modern one. I think that was the Golden Gate Bridge. Okay, that is also cable stay. Okay, the column here, the main cable and the suspended cable or the secondary cable. Okay, that one is on the bridge, still cable stay. This one is far more advanced. Okay, we are not going that far yet, but in the end, it still rely on these cable forces. Okay, and these are reasons we have to go through in the series at this course or the schematic first, right? This is the way the normal structure is. Okay, there will be the main columns, right? It could be on the bank depending on the situation, right? Like the first one, the column is on the bank. Then you have the main cable running through there, the pavement where the road running on, okay, and then of course the cable, the suspended cable to take the force onto the main cable, back to the column and to the anchor. Okay, or sometimes this is schematic by the loading, because whatever the road running on the road, the weight will pull down, right? The road will transfer to the suspend cable, pulling it down. So this cable is in the tension mode. Okay, pass on to that cable, the main cable, which pass on to the column and the anchorage. Okay, so that's the whole schematic scheme. Of course, if it kind of like this one is, well, I want to say simple, but it's not simple, but schematically it's quite simple. The idea is quite simple. Compared to the last bridge you see where the cable is in inclined angle, changing inclined angle, that is even more difficult. Okay, but nevertheless, these are the basic subject. So we learn the basic we need to know. Usually in this type, the study will carry on from beginning the simplest one. There's no more theory, something we already know. However, the calculation have to be kind of flexible. You have to see the picture. Okay, so this is just cable subject to point loads. Okay, sometimes it's called concentrated loads. The idea is that the word point load, it is in theory. There's no such thing that the load can go down with no areas. Okay, it's just usually in a really small area. We assume it's a point, that's all. Okay, so sometimes they call it concentrated load. Then usually in a series, you will carry on to subject to distributed load. This will be next lecture. Okay, then last one, they will talk about the self weight, its own weight. This one here I will not include in the lecture. It's in the third one is in the textbooks. Okay, I suggest you do some certain reading on it. Then let's go for today. As I said, there's no new theory. It's the way we view it. Okay, and today it's more discussion because it's pure axial case. The way we look at it will be similar to the way we look at trusses, meaning we can have the joint equilibrium and the section equilibrium. Okay, this is example. We start from example. Okay, usually the system of cables. Okay, there will be certain unknowns. In this case, the unknowns will be the two reactions here, two reactions here, three internal force, and we don't know the height. That's general. Okay, it could be in a system, but it will be certain amount of unknowns, quite big amount. This one here, because it's just the first thing we look at so far, so rather than discussing the options you can have, we just go through the system for once, and then the second example, we look of more options, what we can do with it. Okay? So the general idea is that if we want to know all this, the simplest one to go is look at, as usual, the total free body diagram and see what we can do with it. Okay? So if we draw a free body diagram, so that's the body. At point A, there will be two reactions. Remember, pin support. It pin support at A, it pin support at D. Right? So two reactions there. Let's say XY, just be simple about it. That one, should it go up or should it go down? That one, the AX, should it go up or should it go down? AY up, AX left or right? How do we think about it? Okay, let's look at joint A equilibrium. Just a point of consideration. Joint A is attached by this rope AB, this cable AB, right? We know that the cable, the rope, cannot be anything else but tension, correct? In this case, it means that that has to pull point A downwards and to the right hand side. Okay, so RAY, as you said correctly, it should go up, but RAX should go to the left hand side, not right. Okay, because it's the resisting that tension, right? But because that one is 2 meters and that one is 2 meters, we know that angle as well, 45 degrees, right? Can I carry on? We accept that. Therefore, RDX should go to the right hand side and RDY should go up, correct? By the same logic. Therefore, that one there and RDX, RDY. Now, with this type of learning, with this type of calculation of this application, you will always end up with no part of the body that you can get 3 equations, 3 unknown usually. Okay, usually it's going to be more. In this case, it actually, if you look at this picture, it's 4. Right? Apparently, there are some other pictures that you can look at that you can have only 3 equations. Okay, but we discuss it later. At this moment in time, there's some other choice we can look at. If we realize the picture, we need 1 more equations. Correct? Well, if we go back and look at joint A again, there. Sorry, I forgot to get out of sequence. That one. Notice that this one here, the right hand side picture, you have 3 equations, correct? The left hand side is a joint, a point, you have 2 equations. So the 2 pictures combined, you have 5 equations. We accept that? Okay. In that case, the unknowns we have is 1, 2, 3, 4. That one already counted, and that one is 5. We just said we have 5 equations, we have 5 unknowns, the system can be solved. Right? So basically this one here, the right hand side picture is a thing that we usually call section method. The left hand side is the joint method. In this case, you need the 2 to combine to actually solve it. Okay? Start off, sigma moment about point D equal to 0. This one, notice the drawing, point A and point D is on the same level, right? Meaning RAX will times 0. Okay, that's the whole equations. Then in this case, we can solve RAY immediately. Okay, and then sigma FY will give you RDY, of course. This is still on the right hand side picture. I mark number 1 and number 2, so we know the sequence because we're going to jump from left and right. Okay, there are 2 free body diagrams we have to jump. Sigma FX, clearly you can't do anything with it yet, so we leave it for now. We go to that free body diagram then. Okay, sigma FX or sigma FY first. RAY, we already know it, correct? So in this case, we know that angle. Then sigma FY would give us the value of TAB. Right? There we are. It's in tension. That. Then from that, once we know TAB, we know the angle. Sigma fx should give us IAX. Okay, and then of course we can come back now to do sigma fx on this side, and then we get all the reactions plus TAB, right? It's getting more fun, isn't it? Well, in this kind of application, I suggest that you keep one picture in hands and keep updating information, because we will need this information to keep continuing. Okay, so if we update our free body diagram, it should be in that picture, right? That 18 and that 30 is already been told. We calculate RAX, RAY, RDX, RDY, and we know tension in AB, right? So if we look at this one, apparently you could go to joint B or joint C. Any joint would do, because there is only 2 unknowns per joint now. Okay, I will point out the unknowns. Let's say we go to point B. Oh no, we go to joint D first, sorry. I jump, we got that, we go to D first, sorry. D is easier. Apparently C you can't do it yet, my mistake, apology. Actually we go to point D first, okay? There we are. That one, apparently there's not only one unknown. Point D has 2 unknowns. The first thing we don't know about it is, of course, tension in CD. The second, we don't know that angle either. Correct? Therefore, that one theta is in red letter because we don't know it. And now the thing is that when we calculate forces, remember, we need to talk about the angles all the time, taking cosine and sine, right? Not knowing angle is a problem. So it's unknown. But 2 unknowns, 2 equations, we should be able to solve it. Don't know what to do, sigma fx, then give you that equation. Sigma fy, give you that equation. What do we do then? Yeah. The system of equation, if we want to work out for theta, right? You have one in sine, one in cosine. Okay? So then you can use the equation is actually 8 divided by 7, I think. Sine over cosine. My apology. Mistake again. Hang on. Sigma fx cosine, sigma, yeah. It should be 8 over 7. Okay? And then it's 31 over 17. Sine over cosine tan theta. TCD and TCD cancel out. Right? If we end up with that, then we can work out theta. Right? What next? How do you find TCD? Okay, we could substitute theta, yes. Okay. Usually what they do is they try not to rely on theta to calculate TCD. Could you calculate TCD without knowing theta? Apparently they use the relationship of sine square theta plus cosine square theta equal to 1. Okay? You square up this equation, and you combine them. This is what you get. Okay? Take the component out, then you will have TCD square in bracket cosine square plus sine square equal to 1. End up that equation. Okay? Meaning you can work out TCD without knowing theta. Okay? Either way should give you the same answer if you got it correctly and with enough digits. Okay. Well, we done this one, we update the free body diagram. Right? So we work out TCD, we work out the theta. The question also, usually the question will ask for the H value as well. Okay? we know if we look at this triangle here, we can actually work out the value for h. That's the triangle. Okay, that side is 1 meter according to that. That is h, that is the angle. So using tan value, right? In this case, we can work out h equal to 1.824. Okay. Now we're gonna move on. This time, joint B and joint C will be the same thing. Okay, 2 unknowns. Or is it 1? I think it's maybe 1, part 1. Apparently, before we go to, let's look at joint B. Okay, apparently, once we know that h, we can tell that angle. Okay, let's look at this triangle BC and the horizontal line. We can draw that picture. Correct? Let's call that angle alpha. From here to here horizontally 3 meter. That height, from here to here 2 meters. From here to here 1.824. The difference therefore 0.176. Correct? Therefore, you could actually work out alpha. So the angle is not the unknown. In this case, for this one here, we can work out the angle beforehand. Okay, once we work out the angle, the rest is the same. Drawing the free body diagram. Sigma fx, then we get T BC straight away. What do we do with sigma fy then? We get all the answers. As I said, this is the same mentality with the trusses. We tend to have 3 equations left for checking. Okay, so then we can continue with the check. Sigma fy, then you get that form of equation. Apparently, if I work out to the 2 decimal point, that will be the number, which is exactly 0. Okay. Joint C, we'll update the information we have first. We have everything. Joint C haven't been done. So again, supply 2 more checks. There we go. Just the free body diagram, everything is known. Sigma fx looks okay. Sigma fy again looks okay. And which means in fact, when I did it, admittedly, I did something wrong. But this one actually tells me that I have to go back and check. Okay, so that's summary. Example 2, however, decide to actually discuss with you guys. Okay, so let's see. This one is a little bit more complex because I don't want to get any numbers out of immediately. But this is the usual case. When we show you the bridge, notice that there is no guarantee that the cliff on both sides will be the same height. Meaning your support might not be on the same height. It could be on different height, correct? So therefore there is no guarantee that the support on both sides will be on the same level all the time. Okay, so in the end, support will move up and down according to situations that you might not be able to control. That's it. Okay, so there we are. Now this point A and point D, the weight is the same weight, dimension horizontally the same. Okay, that one will drop down 1 meter, point D. Okay, the height h is usually guess, meaning I don't know whether it's actually come down below B or not. It might be higher than B. We just guess it. The calculation will tell you where it should actually be. But in this case, just to cut the explanation short, discussion short, we'll just talk about how to find reactions. Okay, and of course the tension, then you can carry on with the other equilibriums. Let's look at the free body diagram first, the usual one. 4 of them. The one we actually do is adding in the joint A equilibrium, right? Like last time. We could still do it, but this one here we have 3 equations. We have 4 unknowns. Okay. So, like last time, if we want, notice my word carefully. And the word is if we choose to solve point A first. In this case, RAX, RAY. Okay? Then I think the easiest picture to add in is joint A itself. Okay? Will be similar situation like last time. And then we have, of course, 5 equations, 5 unknowns. It doesn't have to have all 5 equations, 5 unknowns first before you solve it. If you can solve one by something first, then you do it. But the whole series is 5 equations, 5 unknowns, that's all. In this case, apparently, we cannot calculate any direct number yet. So what we do is, as I said, this case, we choose to solve at A first. So the first equation may be making moment about point D. Okay? That one is the first one we should take, and it run out like that. This time, RAX doesn't disappear because there is a distance of 1 meter here, right? So we have RAX involved. Arranging it, then we have that equation. Since it comes first, let's call it equation 1. You could try to do sigma fx, sigma fy, but it doesn't help because you add in more unknown as well, right? So maybe we go to that one. Okay? Sigma fx, then we have that equation. Sigma fy, we have that equation. That one apparently can use to state relationship between RAX and RAY. For example, I could use 2/3 or 3/2. Then I will have RAX over RAY on one side. The other side, because sine theta, sine 45 and cosine 45 is equal, on the right hand side will be 1. In other words, it means RAX is equal to RAY by number, not direction, just by number. Okay, by the size. If RAX and RAY are equal, that equation then become 5 RAY equal to 1 or 2. Correct? Which means I can solve for RAY. Once I solve for RAY, then I can solve for RAX. Notice that the linkage, even though RAX equal to RAY, but we are talking about scalar value. So here we are not talking about direction, we're talking about numbers. Correct? So meaning it is actually equal by the size. However direction, it will have to go back and obey the drawing. Okay? RAY positive mean going up. RAX going positive, going left. There we are. RAY positive going up. There we are. Once we know RAX, RAY, then this picture can be solved. Correct? Sigma fx and sigma fy, or you can do sigma moment at point A if you want, but there's no need to do it. So we complete the whole picture, all the reactions. Okay? Well, how about going back to the same picture? This is about choices. Apparently, you don't always have to do that. You could choose something else. How about that one? Free body diagram from joint B to joint D. Count carefully. How many unknowns? 3. We know the angle. If we choose wisely, we know the angle too. We know the height. 3 equations, 3 unknowns. In fact, this picture can be solved before that one. Okay? However, since this question only requires reactions, I don't want to solve for TAB. If you want to solve everything, I suggest you do this one. I would have done this one myself. Okay, but because I want to solve for only RDX, RAX, RAY, RDX, RDY, so I use both together. But just so that we realize, this one have 6 equations, 5 unknowns. Okay? Count. I'm not lying. Count. You can count. Okay? Meaning, because that one can be solved in itself, right? That one cannot. However, I can use those two combined to solve these two and these two without having to find TAB. Okay? I have to shrink it a bit because I don't have space. Okay? Make it a little bit smaller. I will go the same route. This one here, if I want to solve reaction at point D, taking moment at point D would defeat it, because I will have AX and AY again. So of course in this case I would have to take moment at point A, right? And we work out, well, blah blah and blah blah, and then you get that expression. Then we go there, we take moment about point B, then we have another expression again, AX and DX and DY. Look at that pair. I think the easiest one to go is just combine them, right? So there we are, equation 1 plus equation 2, then that one disappear, that one become 10, that one become 276, divided, then we got that one. Okay? Now you can substitute that into that equation or that equation and get dx. It's not reliable, because again, the more you calculate, the more mistakes you can make. The other way you can look at it is that I will use 4 times that equation and then 6 times that equations, and then set one up minus the other one. In this case, I will eliminate RDY and calculate for RDX, and that is the answer for that. Or if you did it correctly, you can substitute RDY into 1 or 2. You should get the same answer. Okay? Then of course, once we know RDX, RDY, then we can find sigma fx, sigma fy. Which one is better? It is up to what you like. It is how you see it. Because in the end, as I said, if you do it correctly, the 2 set of answers will be the same. And here we are. We haven't got anywhere far yet since we start the second half. After the midterm, all we have done so far is sigma fx, sigma fy, sigma moment, isn't it? Okay? So this is nothing new apparently. It's just we have to see the picture for ourselves. Practice makes perfect. Okay? Questions? The first question will be very similar to the example, so not really challenging. Number 2, we just to get you starting. Okay. Number 2 will be more challenging, and maybe we can discuss a bit more when you get to that question.